What are the types of diaphragms? Well, we got concrete slabs, composite metal deck slabs, or composite metal deck by itself, as we talked about. Precast elements with or without concrete topping slab. I think many of you have heard of the staggered truss system that AISC promotes as a viable structural system for condominiums and hotels. That's a good example of a system where diaphragms are playing a major role in the satisfactory performance of that system. Untopped metal decks, like roof decks, have to act as diaphragms to distribute the in-plane wind shears or seismic shears over to the lateral load resisting elements. And even in apartments and residential construction, plywood sheathing is very common as a diaphragm, both in a vertical plane and also in a horizontal plane. One thing that's very important to understand, if you don't know this, that standing seam roofs that are very common in metal building types of construction, they're very light decks that span vertically up steep slopes, usually to shed rain and snow. Those do not have any diaphragm capacity because they're really they're like a system of linear elements that really don't have any shear transfer capability. They're only good for carrying vertical load, basically. And therefore, anytime you see the word standing seam roof, you need to say no diaphragm. The diaphragm has to be provided by something other than the metal deck, and usually it's horizontal rods. Rod bracing is very common in those kinds of buildings, or angles or T's. I know when we've used standing seam roofs as an architectural requirement, we've had to put our own horizontal diaphragms into those roof systems, which can be kind of expensive, because usually you're weaving steel in between bar joists or under purlins or over purlins or through purlins, and so it's no fun to erect that stuff, and it tends to be very expensive. Rigid diaphragms distribute horizontal forces to the VLLR elements in direct proportion to the relative rigidities of the vertical lateral load resisting system. The diaphragm deflection is insignificant compared to that of the VLLR elements for a rigid diaphragm. What do we mean rigid diaphragm? Like a concrete slab, pretty rigid in its own plane, very stiff in its own plane. And the horizontal forces it distributes are going to be basically in proportion to the stiffness of the supports, which in this case are the vertical lateral load resisting elements. Examples: composite metal deck slabs or concrete slabs are generally, under most conditions, rigid. At the other extreme, there's flexible diaphragms. They distribute their horizontal forces independent of their rigidities and more by tributary area. You can think of it as a contiguous beam on an elastic foundation, is a good analogy. Mostly the load's based on tributary area. The diaphragm deflection is significantly large compared to that of the vertical lateral load resisting system. What's an example? Well, an untopped metal deck slab under some conditions, or plywood, might be a flexible diaphragm. Many engineers just assume plywood diaphragms are flexible, and their shear in them is proportioned basically by tributary area as opposed to by rigidity. And then, of course, there's a whole world of decks that are in between. And as you're going to see, whether it's a rigid element, a rigid diaphragm, or a flexible diaphragm may be not only a function of the material, a metal deck or concrete slab, but also the spacing of the vertical lateral load resisting elements plays an important role as to whether a diaphragm is rigid, flexible, or in between, which is semi-rigid. Okay, the IBC 2003 and also the 2006 edition do define what is a flexible diaphragm. The diaphragm shall be considered flexible when the maximum lateral deformation of the diaphragm, looking in plan, that's that delta D dimension right here. That is, the yellow line represents the deflection of the diaphragm as a horizontal beam. Considered flexible when the maximum lateral deformation of the diaphragm, delta sub D, is more than 2 times the average story drift of the associated story. The drift of the associated story in this case would be delta VLLR. So when delta D is 2 or more times delta VLLR, the diaphragm is flexible. That's just sort of an arbitrary definition that the IBC has come up with to differentiate the requirements for rigid diaphragms compared to flexible diaphragms. It turns out the Steel Deck Institute has its own classification based on stiffness, shear stiffness of the diaphragm. Shear stiffness of the diaphragm, and you'll see this in equation form in a minute, but this shear stiffness of metal deck diaphragms has come to be known as G prime. You're familiar with G, the shear modulus of elasticity, which is E, the Young's modulus of elasticity, divided by 1 plus Poisson's ratio. Well, G is the shear modulus of elasticity. G prime is related to G, as you'll see in a moment. So, armed with that, here's the Steel Deck Institute definition of a flexible, semi-flexible, semi-rigid, and a rigid diaphragm, all the function of G prime, the shear stiffness. These are just guidelines, and there's no right answer or wrong answer. They just sort of give you a feel for what's flexible and what's rigid. Now, let's take an example here of a 250-foot long building with a 50-foot width that has 5 shear wall systems in it. It's labeled the VLLR. In that case, the diaphragm aspect ratio is 250 divided by 4, whatever that is the span, and the depth of the diaphragm is 50. So it's a pretty deep element for its span, right? That is one stiffness situation for that diaphragm. Here's another one. If you use the same metal deck, the same building geometry, but instead of 5 lateral load resisting elements, we only had 2. And now the deck diaphragm is spanning 250 feet for the same 50-foot width. Clearly, the spacing of the vertical elements is a function of whether a diaphragm is rigid or flexible, not just the material. So keep that in mind when you're thinking about how to model a diaphragm. If you have your lateral load resisting frames at 30 feet on center and your building's 100 feet wide, you don't have much diaphragm deformation going on there. And so you can assume the diaphragm's rigid and march on. But if you have this condition right here, where the aspect ratio of that diaphragm is 250 divided by 50, or 5 to 1, let me assure you that that's a flexible diaphragm, and you need to model it just like a beam, because it's going to deform in shear deformation and flexural deformations just like a beam would. So the moral of the story is the spacing of the lateral load resisting system is a player in determining whether a diaphragm is flexible or whether it's rigid. Let's talk about some terminology that's common in metal deck jargon and publications that deal with diaphragms. Obviously, you got the vertical lateral load resisting element, which is the receptor of the diaphragm shear. That's where the shear ends up, going down the vertical lateral load resisting element. There's this thing called the drag strut. The drag strut being an element within the lateral load resisting frame itself. It's connecting one end of the system to the other that's receiving diaphragm shear. That's called, in diaphragm circles, that's called the drag strut. The collector beam is another term you see a lot. That's an element that's in front of or behind, but in the same plane as the vertical lateral load resisting system, and it's also receiving diaphragm shear that's collecting it, hence the name collector, and then transmitting it along its length to the vertical lateral load resisting system. It's called a collector beam. Then, of course, you have the chords of the diaphragm, either the tension cord or the compression cord, which are taking the chord forces, if you will, of the diaphragm. And then you have the field of the diaphragm itself, which is carrying all the shear. whether it's a concrete diaphragm or a metal deck diaphragm, all the shear from that lateral load you see at the bottom of the screen, all the shear in that diaphragm is carried by the field of the diaphragm in shear. Okay, one important thing to remember is that the way a diaphragm feels forces from wind and the way it feels and forces from seismic are totally different. For seismic, the code actually has diaphragm shear equations and tells you how to distribute the diaphragm shear from the field of the floor into the diaphragm. And as you might expect, it's proportional to the mass of the floor, or it's a function of the mass. Wind, however, is really more of an external loading as opposed to inertial loading. And usually wind shear gets into the diaphragm just as a line load on the perimeter of the building. The cladding might span vertically, right? It's receiving the wind load, spans vertically to the floor, and it loads the floor diaphragm up as a line load along the length of the diaphragm. Totally different way that the shear forces are felt under wind compared to seismic. And what you really have to be careful about is condition C there. Any shears that come into the diaphragm because of offsets of the vertical lateral load resisting system. I'm going to show you a slide here of this in a minute. Whenever you take a braced frame down in one plane and then move it over to another plane, all of the shear that was in that frame from above has to go into the diaphragm over into the new planar location of that vertical lateral load system. And those shears can be very, very significant because they're collecting all of the wind or seismic shear from above that floor to the very top of the building. So you have to be very careful of that condition. You can treat a diaphragm just like a deep beam. In simple cases like we have here, it's just a simple beam spanning from one end to the other, one support to the other. In this case, the support is the vertical lateral load system. You can have a shear diagram and a moment diagram that can be used to proportion the shear stresses and the flexural stresses in that diaphragm. So just think of it as a deep beam. Now, let's talk about how the diaphragm shear gets its way into the vertical lateral load resisting system for different kinds of situations and basically different degrees of shear loading from an earthquake. In the simplest case, if you have the building loaded with wind load, like there at the bottom, or inertial seismic force, we're loading up the diaphragm with a line load, and then all that shear that it's collecting has to get its way into the vertical lateral load resisting elements labeled brace A and brace B. In the cases where the line load on the diaphragm is relatively small, you can find that you're able to deliver the shear directly into the lateral load resisting system along this length without having to rely on any of this here to drag the load over. That is, the shear is low enough where you can take it directly into the vertical lateral load resisting system itself. That's the simplest case. If you look at this in elevation, there's your brace frame over there. You're dragging all that diaphragm shear only over the width of the lateral load resisting system, and that shear is small enough where the diaphragm can resist it without a shear failure. This is typical of what you would find in a wind load condition. Diaphragm shears aren't very big. This is not a problem. Matter of fact, it's so little of a problem we don't even pay attention to it. However, when you get into high seismic zones, when the big buildings that are big masses and you can get some really heavy seismic shears generated, you may not be able to resist all the shear within the width of the lateral load resisting system by itself, and instead we have to rely on additional width, these collector beams, to help carry or collect some of that shear. If you look in elevation, in that condition, You might have a situation like this. Here's our tributary width of the brace frame. If you tried to carry all of the shear in that width, the shear is too high. The metal deck or the floor slab can't carry it. So we got to rely on this area to collect it. Once it's collected in this beam, then it's got to get from here all the way over to here so it can get down to the ground. That's why you call that the collector beam. It's collecting the shear, delivering it through the beam column joint, across the other beam, down into the lateral load resisting system. That's the second condition, sort of an intermediate condition. Now, if you really get high shears, like you might have when you transfer a vertical lateral load resisting system, or if you really have a heavy building in a heavy seismic zone, you might need the whole tributary width of the building to carry that shear, to keep the shear stresses low enough. And now we got two collector beams and a drag beam that are taking that shear and delivering it to the lateral load, vertical lateral load resisting system. Now in those conditions, you got to be real careful that when we deliver the diaphragm shear into that beam, it goes through the connection into the column, out the other side, and the connections are able to carry that, because that's how the load's getting over to the brace frame. So that's why you got to always create a load path in your mind on these diaphragm shears to be sure that all the collector beams and their connections are able to carry these shears. Now, special conditions occur when you have joists or purlins. In the case of a joist, the joist seat unfortunately creates a gap, right, from the concrete slab up here and the steel beam that's down here, 2.5 inches or 5 inches, depending on what kind of a joist you got. So now we got to worry about, wow, the load's up here in this plane where the concrete is, and the steel beam's down here, and the load's got to get from this level down through the joist seat into the beam over to the vertical lateral load system. Well, those joist seats are only capable of carrying so much, and not a whole lot, as you might expect. We're talking about hundreds of pounds here, not thousands of kips. So in the book that Jim Fisher wrote, Designing with Steel Joist, Joist Girders, and Steel Deck, written for Volcraft, he talks about the shear capacity of a joist seat to be able to do this. And many times what you're going to find is, except for light wind zones where you don't have big shears, if you're in a heavy seismic zone where you have high diaphragm shears, you're probably going to have to supplement the joist seats with some kind of filler element to help carry the shear from the level up here down to the beam down here. That filler element can either be an angle, or it can be a piece of a tube, or it can be a channel, a filler channel. All of those elements can be used to supplement the shear capacity of a joist seat. But in our long span roof business, when we're collecting big wind shears into the long span roof and carrying them over to the ends of the building, and we have bar joists as the roof material, we're oftentimes having to put in filler tubes to collect that shear down from the diaphragm, the deck diaphragm, down through the bar joist seat into the purlin over to the lateral load system. So be careful about that. If you forget that, and you get a high windstorm, you might find yourself with a diaphragm failure. And indeed, there's been very clear evidence of this occurring in high seismic zones in earthquakes, where the diaphragms just haven't performed because there wasn't a valid load path to get these shear loads where they needed to go. Some other situations you need to be on the lookout for is when you have big openings in your floor. As you can imagine, this diaphragm receiving its load, line load along the bottom here, just like a beam, and then it's got to carry that beam shear over to this point where the vertical lateral load system is. It's kind of like a cope of a beam, right? You got a sort of a shear concentration of force right in that coped area, and that may require some additional reinforcing steel right here to take the bending in that dapped area, and then you got to check the shear in that distance D. Be sure that your shear isn't too high. If it is, you may have to reinforce the diaphragm along that area. So be watchful of openings in diaphragms. They can create high shear situations. Here are some simple equations for simple diaphragms. These are basically rectangular diaphragms. The bending deflection is nothing more than the simple beam deflection you're used to, 5W, well, 5Q L to the fourth, or 348 EI, where EI is the stiffness of the diaphragm in plane. Most often shear deformation or shear deflection dominates. Because the diaphragms are so deep, usually the flexural deformation is minuscule, and delta sub S actually controls, and for a uniformly loaded shear beam, it's QL squared over 8B TG, where T is the thickness of the deck, B is the width of the deck, and G is the shear modulus that we talked about earlier. This might be a good time to point out that the combination of T times G is what's identified in the metal deck catalogs as G prime. T, the thickness of the deck, times G, the shear modulus of elasticity, is equal to G prime, known in the metal deck catalogs as G prime, or the shear modulus. Okay, if you look in the metal deck catalogs, either the Steel Deck Institute catalog or the Volcraft catalog or anyone like it, you'll see equations and tabulated values for G prime. And here's examples of what those equations look like. The one on the top is the general equation developed by Luttrell at the University of West Virginia, where G prime is a function of ET 2.6 S over D plus phi D sub n plus C. All of those terms account for the deformation of the deck. That deformation partly comes from connection slip, it partly comes from warping, and it partly comes from just sheer deformation of the sheet itself. All of those parameters are reflected in that G prime equation. What Volcraft has done is they've taken that top equation that's in the Steel Deck Institute manual and they've simplified it into terms that they tabularized in their catalog. So you can find that alpha, the D sub x, and the K term in the catalog, as well as that K2 term. If you're evaluating the deformation or deflection of a shear diaphragm, you need that G prime value. Depending on how you weld or connect the metal deck diaphragm to the purlins, Volcraft publishes the G prime value that's appropriate to how you connected it to use in your analysis to determine how much the diaphragm deflects. If you have a filled diaphragm, not just a metal deck diaphragm, the equations look similar, only now when we fill it, we take away the warping part of the term, right? If you fill a deck, you can't warp the deck anymore because the fill prevents that warping. So the equation simplifies a little bit. And here's the way Volcraft identifies that same equation for the case of filled diaphragms. G prime is equal to K2 over alpha plus 3K times the span plus the term K3. All of those are tabularized in the metal deck catalog. What is the definition of that shear modulus term G we talked about? Well, remember it's E over 2 times the quantity 1 plus Poisson's ratio. G prime is equal to that G term times the thickness of the deck. That's a fundamental property of a metal deck, is the G prime term that you see tabulated in the catalog. And as I say, usually the shear deformations control over the flexural deformations simply because the decks are so deep in their own plane. The metal deck strength, in addition to stiffness, which is a function of G prime, we have a strength term that has to be evaluated. That is, how strong is the diaphragm to carry the shear forces. The metal deck catalogs identify that metal deck strength as shear strength S. It's a function of the edge fastener strength, the interior panel strength, the corner fastener strength, and shear buckling strength of the metal deck itself. Those four phenomena control the strength of a metal deck diaphragm, and all of those are calculated and tabulated for you in the metal deck catalogs in terms of pounds per foot, pounds per linear foot of attachment length. So you'll look in a catalog with a certain deck fastened a certain way, and it'll say S is equal to 290 pounds per foot. That means 290 pounds of shear can be transferred for every running foot of metal deck attachment to the supporting beam. And typical values of that strength range from 150 or 200 all the way up to about 1,200. You can't really carry much more than 1,200 pounds per foot of shear in any metal deck without strengthening the deck. There are fillers that you can put in the deck that increase their capacity that they use out in California for high seismic zones, but generally most metal decks have 400, 500 pounds per running foot of shear capacity in their normal state. Now be careful of whether or not your metal deck catalog gives you shear values in terms of LRFD strengths or ASD strengths. Obviously they're related by a safety factor, and different manufacturers and different researchers have attached different safety factors and fee factors depending on the conditions. Unfortunately today I don't think there's a standardization of fee factors and safety factors. So you got to be careful. I think the IBC may have its own safety factors and fee factors that it uses, so those probably would control if you're using the IBC. Anyway, to give you an idea, the safety factors are pretty healthy. They range from a 2.75 all the way up to 3.25, depending on whether it's welded or screwed or a filled diaphragm. Safety factors are kind of high in recognition of the scatter of the test results. Remember also in that underlined note we have here that sometimes that the catalog strengths are already increased to 1/3 under ASD for wind, and so you don't want to take that increase twice. Be careful to read the fine print. Many catalogs are now coming out in terms of limit state design or LRFD design, in which case the results are given in terms of the capacity, and you got to use a fee factor, and therefore depending on which manufacturer and who you go to, you might get different fee factors for different conditions. So be on the lookout for that. Again, this is discussed at length in this diaphragm design manual by Larry Luttrell from West Virginia University. He's the one that received the commission to do the research on behalf of the Steel Deck Institute. Again, different fee factors for different conditions. Be sure to look in whatever code you're using for the appropriate fee factors for your condition. If you're going to use the concrete slab as your diaphragm element, and you don't want to count on the metal deck if one exists, or if you just have a concrete diaphragm, obviously ACI 318 in Chapter 21 does have shear strength requirements for diaphragms. And there's an expression in ACI equation 2110 is the nominal shear strength for a concrete slab diaphragm. You can use that and reinforce the diaphragm appropriately with horizontal and vertical bars in the plane of the diaphragm to reinforce it to carry the nominal shear stress that you calculate. Metal deck diaphragm terminology, they kind of have their own jargon, and we try to show that in this slide here. The light horizontal lines represent flutes, okay? The yellow circles represent bottom of flutes over a support where you would make a attachment of the metal deck to the dotted line below, which is the purlin or the beam. The horizontal red broken line is the edge of the deck sheet, where you have the vertical or the triangular attachments which are called the side lap fasteners. So you got the deck panel spanning from purlin to purlin. You got the support fasteners, it's the round circles. And then you have the side lap fasteners, which are the triangular symbols. And of course, the span of the deck is nothing more than the span between purlins. So this is the way the metal deck catalogs identify it. Now, they have their own terminology. You see in the metal deck catalogs for a sheet that's 36 inches wide, if you connect it 3 times at the support across that 36-inch flute, or that 36-inch wide sheet, it's called a 36/3 pattern. It's connected at each edge and 1 time in the middle. If you connect it 4 times, it's 36/4. And so on. If you connect it 9 times, it's 36/9. And since you don't have 9 flutes, you double up on the end flute. So the 36 inches is the width of the sheet, and the 9, 7, 5, and so on is the number of connectors. This is what you're going to see in the metal deck catalogs when it lays out the fastener requirements. And remember, depending on whether you do 36/3, 36/5, 36/9, that dictates how much shear per running foot you can transfer from the field of the diaphragm down into the purlin. That and also the number of side lap fasteners. So the side lap fasteners in this cross section are denoted by X, and then the end fasteners are noted by the round circles. The Epic catalog, where they have those special profiles to carry the hangers, they have a little bit different kind of notation. As shown, notice that their side lap fastener is above the plane of the deck, not at the floor of the deck, so it's a little bit different animal. Okay, we're going to talk about the diaphragm chord forces. Just like any beam, when you flex it, you create tension in one flange and compression in the other flange. In a diaphragm, those are called the chord forces. You have to design your diaphragm for those. How do you do that? You either put an edge angle on there and design the edge angle as continuous at the edge of the diaphragm to collect that chord force, or you can fasten the deck to the spandrel beam and have the spandrel beam serve as the chord element. If you go that direction, remember that when the spandrel beam ends at the column, you got to carry that additional force through the connection, through the column, into the other side. You got to be mindful of the spandrel beam connections if you go that route. Many times what's done is you either provide an angle that's spliced along the length above the purlin so that you can do it on top of the deck, or if it's a concrete filled diaphragm, a lot of times you just put reinforcing bars in there and let the rebar act as the chord element, just like you would a concrete beam. So you got several options there depending on what kind of diaphragm you have.